So today we discuss AC voltage applied on series LCR circuit. Okay. So previous class we discussed the AC voltage applied on a capacitor and also AC voltage applied on an inductor, resistor here. Okay. So here we discuss AC voltage, and that's very important. AC voltage applied on series LCR circuit. Series LCR circuit. Okay. CKT is short form means circuit. Okay. So previously discussed AC voltage applied on series L, series inductor, series capacitor, series resistor. Similarly here the circuit diagram look like this. There's the AC voltage. There's the L means inductor. Okay. There's the capacitor and that's the resistor. Okay, there's a LCR series LCR circuit. There's a AC source, so that's the EMF. There's a function of T that is equal to V, that is Vm sine omega T. The function of time here. Okay, so solving with the help of KVL, Kirchhoff's law. Okay, so KVL, so that is a Vm sine omega T. So here applied same KVL, Kirchhoff's voltage law, that is equal to potential drop across inductor, that is L di dt, plus potential drop across capacitor, that is Q by C. What is Q? Q is a charge stored in that capacitor. Q is a small q is a charge stored in that capacitor. That's the Q. Now plus potential drop across R, that is equal to V equal to IR, that is a I times R. Okay, that's the equation here. Now solving with actually solve current. Okay, with the help of phasor diagram. With the help of phasor diagram, we solve current with the help of phasor diagram. Okay, solve current. So actually voltage to jump current. Okay. Why not solve it analytically? Because the phasor diagram is easily you can solve this. Okay. So that's a message. You can also solve it analytically or with the help of graphically. Too much method here. Okay. So I choose a phasor because the phasor is easily to solve. Okay. Solve these. So with the help of phasor diagram, derive the current expression here. So phasor diagram solution. So now the phasor diagram solution. There's a diagram solution. Okay. So now you see that. So now first we draw a current diagram because the current phasor, because the one single current passing through that L inductor, capacitor and resistor, because there is no node here. Okay, so no junction point here. So that's why the current in series, so all are in same. Okay, so that's why current is a single. There is a single current here, but potential will be different here because the series, so current value will be the same. Now the potential will be different here. Okay, so here the potential drop across resistor, suppose say call VR, because we know that from previous class that is a potential drop across R and current are in phase, no phase difference here. So that's why they are overlapped. So there is no phase difference, voltage or current. Okay, both are in same, they are in phase. So now potential drop across L inductor. Okay, keep in mind this inductor here, that's a VL, potential drop across inductor, that's a lead. Okay, pi by 2 ahead of current. Now and the potential drop across capacitor, okay, VC, okay, that's a pi by 2 behind the current. Suppose that, so the rotation is omega t plus phi. Phi is the phase angle. Phi is the here is a phase angle. Okay. Now, okay, there's the anti-clockwise rotation here. Now I extend that. Okay, help of these. And the first we draw the three phase. Okay, voltage phasor. The voltage phasor of R, that is a VR. They are vector. These phasor are obviously phasor is a vector. You know that phasor is a vector. Okay, so that's why direction is very important. Keep in mind. Okay, the direction is very important here. There's a VR. Okay, and suppose that these are the called VRM, the maximum. These are VR, and this length is VRM maximum. Okay, now there's a VL in that direction. Now opposite of VL in that direction, the opposite is VC here. And if VC in that direction, VL in opposite direction, so that's why if I draw VL in that direction, so that's a minus VL, because the VL in that direction. These are the parallel. Now to the opposite direction, that's a VL vector, that is a minus. Okay, and suppose if I vertically add it, so that is a VC plus VL here. Okay, so now apply the vector triangle law here. Okay, there's Vm, final V, or called resultant vector V. Okay, and these gap actually, these gap is, okay, and these gap, that is equal to Vc minus VL, because VL in opposite direction. So Vc plus VL, obviously actually the Vc plus minus of VL, because there's opposite direction, that is a Vc minus VL. So here VCA maximum minus VL maximum, here we choose VL maximum here. Okay, that's the VL, these are the VLM, and that's the VCM, this length. Okay, VCM minus VL here. Okay, this gap, and now you see that there is omega t plus phi. So this angle, the final V, that is a omega t, and this angle be the phi here. So that's why this total angle is omega t plus phi. Okay, that's the phasor diagram here. Okay, so show here the phasor diagram show relation between VL, VC, and VR. So relation between VL in the voltage phasor across inductor VL, VC, VR. These are three voltage phasor. These are the inductor voltage phasor, that's a capacitive voltage phasor, that's a resistive voltage phasor. Okay, clear? Now for analyze these, so these are small VL, small VR, and VC are the voltage drop across that. If I consider that's the small amount of these, so VL, the VC, and VR, these three are voltage drop across inductor, capacitor, and resistor. These are voltage drop across inductor. These are the inductor, capacitor, and finally resistor. Okay, now the first circuit, okay, you keep in mind, please recall the first circuit. First circuit is a voltage, AC voltage applied on a resistor, so there is a no phase difference here. Okay, they are in phase, so that is a V and I, so no phase difference, they are in same phase, voltage and current. But here in case of inductor, when AC voltage applied on inductor, so there is a phase difference. Okay, so here is a phase difference. So you see that voltage drop across inductor is a pi by 2 ahead of current. So here voltage drop across capacitor, there's also pi by 2 lag of current, and current be the same current because these are in series. So we know that from KCL, for network theory, the in series there no current change. Okay, in series the current value be the same. Current value change when there is a junction point. So you see that this circuit is a no junction point here. So that's why the current value is same. Okay. Clear? So here, so VR and I in phase, VL pi by 2 ahead of I, and VC pi by 2 lag or behind of I. Is I, these three I be the same. Okay. So the phasor amplitude. So VR, VC, and these are obviously these are the VR, and these VC and VL. Obviously these are the capital V. Obviously these three are the phasor of. Okay, these are called the phasor amplitude, or say that is phasor amplitude. Okay, the maximum voltage or in resistor, inductor, capacitor. Okay, so you see the diagram here and carefully that VRM, maximum voltage across the resistor, that is equal to I maximum current times R. So VLM, okay, maximum inductive voltage, that is equal to IM cross times XL, that's the inductive reactance. VCM, that is equal to IM XC. XC stands for capacitive reactance. These are inductive reactance, inductive reactance, reactance, and these are capacitive reactance. Obviously, these two are the frequency dependent. These are frequency independent here. So now the circuit voltage. Now the total circuit voltage. These are actually the mathematics. The total circuit voltage. The total circuit voltage, that is equal to voltage drop across the resistor plus voltage drop across the inductor plus voltage drop across the capacitor, that is equal to total voltage. Okay. So in the help of phasor, that is equal to VR. The phasor means a vector that we represent the capital. Okay, these are the vector. VR, suppose we represent bold. So VR, VL plus VC, that is equal to V. If say that is a phasor is a vector. Okay, the vector sign you put here, but there no confusion here. Is a phasor or vector. Now here you see that this diagram, okay, and is obviously a vector. Okay, now this triangle diagram, okay, this triangle here you see that this triangle, okay, suppose A, B and C, this triangle ABC triangle, draw here and say, suppose, okay, these are the VRM, okay, and here that is equal to VCM minus VLM, and this line which is here, you see that actually this line also be the same, VCM minus VLM. Now that's the final, that is equal to VM. Okay, these two lines are parallel. Okay, and these are the triangle ABC. A point, that point is B, that point is C. Now this triangle, there's a right angle. Okay, and there is a phi here. So that's why we apply the Pythagoras theorem here. So that is Bm, that's the hypotenuse square, that is equal to base square. You see that Brm plus perpendicular square VCM minus VLM. Okay. Now we put the data here. Okay. VRM, VCM and VLM. Okay. From these three expression here, put here. So we get so Im times R whole square. VCM means Im XC Im XL whole square, that is Vm square. Okay, now that's the Vm square, that is equal to, if Im square be the common, so we get R square plus XC minus XL whole square. Okay, so Bm, that is equal to root over of, if there is a square, that is Im square R plus XC minus XL whole square. Okay, so finally expression we get here, that is a Vm, that is Im, here is root over of R square plus XC minus XL whole square. From Ohm's law, okay, that is V equal to R, V equal to I R. So here these expression represent a resistor. Okay, almost look like a resistor, and this is called a impedance. This expression is called impedance, and Z is called impedance. Also behave as a look like a resistor, and SI unit here is ohm. So the Z equal to root over of R square plus XC minus XL whole square, and that's the impedance. This is also the dependent frequency. Okay, because that's the XC and XL term here. Okay, so what is the impedance diagram? Now we draw impedance diagram here. So that impedance diagram, that is equal to Z, final expression, that is Z square, you get R square plus XC minus XL whole square. So this is also look like a Pythagoras theorem. Okay, so now if that is called hypotenuse, suppose these are Z represent hypotenuse here, and these R represent that a base, and this line represent XC minus XL. Okay, and this angle be the phi here. Okay, so see that that's the diagram. Okay, that's the impedance diagram. That's the impedance diagram. Very easy to draw. Okay, if you know the Pythagoras theorem, that's a hypotenuse. That's called a base, and that's called a perpendicular. Base square, perpendicular square. That's the hypotenuse square. Okay, so here now we find that tan phi. Okay, the angle between these two. Suppose that tan phi, that is equal to perpendicular by base. So here XC minus XL by R. Okay, and this is that impedance diagram of right angle triangle. Okay, these are the obvious right angle triangle, and that is Z is that hypotenuse. Okay, basic the Pythagoras theorem. So here is some condition here. So condition is that if XC, the capacitive reactance is greater than XL, inductive reactance, so the phi, obviously these are the phi, is a positive. So phi be positive. So phi be positive means this circuit is totally capacitive circuit. The circuit now capacitive circuit, fully capacitive circuit, and if XC is less than XL, so phi be negative. If phi be negative, so XL will be the large. So totally inductive circuit. This circuit is totally inductive circuit. Okay, clear. Now we draw a phasor diagram of voltage and current. Now we draw a final phasor diagram of current. So final phasor diagram of current. The phasor diagram of voltage and current. Okay, so you see that the final diagram is very easy to draw. Okay, suppose these are the final voltage V. Take very small. Okay, voltage V. Okay, and there is a current here. Suppose the current here I, and the gap is these two. Okay, this gap is here is phi, and this angle be omega t1. Now the phasor diagram is look like this. So very easy to draw a phasor. So now that voltage is max here, so max value here. Okay, so choose another point, choose another point here, another point. Try to draw a freehand diagram. That's why it's complicated here. Okay, these are the voltage phasor. So now the current phasor. Okay, okay. So actually the phase difference here is phi. So that the red color represent the voltage and this blue color represent that current. Okay, so here this peak, and here you see that actually that is the current is not look like this. Okay, actually the current is look like this. Like this. Okay, so now these two peak here, the current peak and voltage peak, these difference is a phi. Okay, and now these angle cutting point, and here this angle with the cutting point with the same. Okay, and this point is omega t1. Okay, and we know that the basic that is okay, pi, that's 2 pi. Okay, and that's represent a current, and that is represent a voltage. Okay, that's the basic phasor diagram. The phase difference is phi. There's a peak to peak, top to top point, voltage top, that's a current top. Okay, that's a final phasor diagram. Okay, of series LCR circuit. Now in these phasor, actually keep in mind here these phasor, these are the actual here. XC is greater than XL. Okay, because these are in this direction. Okay, so here these phasor represent XC is greater than XL. Okay, so here is some disadvantage. Okay, so if there is an advantage, obviously there is some disadvantage here. Okay, so disadvantage of technique of phasor. So here some disadvantage of phasor. So disadvantage of phasor, that's a very important. Okay, the first disadvantage is that the phasor diagram nothing to say about the initial condition. So if you see that here we choose the arbitrary T1, in previous class you see that is also when AC voltage applies the inductor, resistor, capacitor, we choose there is arbitrary T1. Okay, we choose the arbitrary value of T. Okay, we say that T1 for solving the phasor representation. The first disadvantage is okay, nothing to say about the initial condition. To say about the initial condition. That's the first demerit of phasor. Okay, so that's why we choose arbitrary t. We choose arbitrary t. One like that. Next disadvantage. So disadvantage number 2. Okay, so drawing a different phasor. Okay, when you try to draw a different phasor with a active phasor is a vector. Okay, keep in mind this phasor means a vector. So is a vector. Okay, so the drawing the different phasor which show that relative angle is different. When you draw a different phasor which show the relative angle between a different phasor is called a steady state solution. Okay, keep in mind this is a steady state solution, not a general solution. Which solution we get with drawing a phasor, this solution is called a steady state solution, not a general solution. Okay, so that's very important. This solution we find that with the help of phasor, this solution is steady state solution. Why? Because the drawing of phasor, drawing of different phasor, different phasor which show relative angle between different phasor and these called steady state solution. These call very important. It's called steady state solution. Steady state solution, not general solution. Keep in mind. Okay, not general solution. These are only a steady state solution. Phasor gives the steady state solution. So there is another type of solution. It's called transient solution. Okay. Here is another type of solution. It's called transient solution. Transient solution. So what is transient? Transient means very small time. Okay, very small. When just switch on or off. When just on or off the circuit. When just on and off the circuit, there is some current. Okay, there is some current. Okay, just on and off, and get some current. This kind of voltage. Okay, and this solution is called just very small time. Very small time. Not only very. There's a very small time. Okay, so this solution is called just on. Okay, or the solution is called a transient solution. So what is general solution now? The general solution now look like the general solution. So the general solution is the steady state solution plus transient solution. Okay, so general solution is the general solution of that circuit, that is equal to steady state solution plus transient solution. Okay, and if you continue the circuit is a very long time or take some time, so after some time, so if you have more time, so transient is die out. Okay, and we only get a steady state solution. Okay, so if some taken a long time for long time consideration, long time, so now if long time, so that's a very small time when you get a transient solution, and time is long, so transient is die out. We only get steady state solution. Okay, so today in the class here, so actually we discuss a very important concept when AC voltage applies series LCR circuit. If you have any doubt in that portion, please ask in comment section. I will try to give the answer. Okay, so next class we discuss more about that in that concept. Okay, in AC voltage, so there is resonance. Okay, there is a power factor. So that's discussed in next class. Okay, so today in the class here. Thank you.